The James Webb Space Telescope has just made an astonishing discovery that challenges our understanding of the cosmos. Could these enigmatic, brilliant objects be the long-sought-after dark matter stars, hidden in the depths of the universe? Stay tuned because a journey into the mysteries of the cosmos has just begun. The James Webb Space Telescope, designed to explore the cosmos' early history, may have captured an unexpected phenomenon. Traditionally, scientists believed the first stars after the Big Bang relied on nuclear fusion, much like modern stars. However, a new theory introduces the idea of dark matter stars, which might have drawn their energy from the annihilation of dark matter particles, illuminating the early universe. These hypothetical objects could have grown to immense sizes, dwarfing our Sun. While dark matter stars were once purely theoretical, the James Webb Space Telescope has detected enigmatic, exceptionally bright, and massive objects dating back to the universe's infancy. These findings challenge conventional explanations for early galaxy formation. Astronomers are now considering the possibility that Webb has observed the first-ever dark matter stars, shedding light on these ancient giants sustained by dark matter annihilation. Let's use Webb's lenses to peer at these potential relics from an uncharted era 13 billion years ago. The James Webb Space Telescope is revolutionizing our understanding of the early universe with its remarkable images and data. One recent discovery, in particular, is both intriguing and baffling. JWST might have detected the earliest dark matter stars. Now let's delve into the enigmatic realm of dark matter physics. Firstly, what is dark matter? In our everyday experience, the visible matter that comprises planets, stars, and galaxies accounts for just 4 to 5% of the universe's total content. The remaining 95 to 96% is shrouded in the mystery of dark matter, an invisible substance that doesn't interact with electric or magnetic radiation, and is detectable solely through its gravitational effects on visible matter. This elusive dark matter forms a vast, spectral cosmic web that influences and shapes the observable universe. To go deeper, dark matter likely consists of exotic subatomic particles with minimal interactions, unlike conventional matter atoms. Dark matter particles don't readily clump or collide, a trait that allows them to smoothly spread out in colossal halos around galaxies, passing through each other rather than sticking together. This unique behavior remains a fundamental aspect of dark matter's enigmatic nature. The leading hypothesis suggests that dark matter comprises weakly interacting massive particles, or WIMPs, which interact weakly with protons and electrons, but do so gravitationally. WIMPs are promising dark matter candidates because of their ultra-low interaction cross-sections, enabling them to remain smoothly distributed as observed. They are predicted to have masses suitable for shaping cosmic structures. WIMPs' crucial property is self-annihilation, allowing them to collide and produce radiation, which plays a role in dark matter stars' energy generation. Although evidence for dark matter exists through various observations, its particle physics nature remains largely enigmatic. Dark matter's lack of interaction with electromagnetic or nuclear forces makes direct detection challenging. Experiments such as the Large Hadron Collider and underground detectors aim to detect WIMPs directly but have not yet confirmed dark matter particles. The mystery persists, despite mapping dark matter's influence on cosmic structures and galaxies across the universe. The question of how dark matter works is intriguing because it doesn't interact with light. To become stars, dark matter particles must efficiently annihilate when densely packed. Annihilation occurs when a particle collides with its antiparticle, converting their mass into energy. For this to happen, dark matter particles must be their own antiparticles, allowing mutual annihilation. Theoretical WIMPs could fit this role. While such events are rare due to limited interactions, in the early universe, high dark matter densities could lead to more frequent collisions. This energy could heat and compress nearby hydrogen and helium clouds. Thus, dark matter stars might have formed in ancient galaxies' cores, driven by these annihilation events in regions with high dark matter density. The James Webb Space Telescope's April 2022 observations uncovered astonishingly bright ancient objects, seemingly galaxies from over 13 billion years ago. However, their brightness and compactness defy early galaxy formation models. Instead, they suggest a different phenomenon: dark matter stars. These hypothetical objects rely on self-annihilating dark matter particles, like WIMPs, densely clustered. This annihilation process releases energy, kickstarting fusion, and creating a luminous object sustained primarily by ongoing dark matter annihilation. It's a novel phase of stellar evolution. JWST's potential detection of these theoretical dark matter stars adds an intriguing layer to our understanding of the early universe. A striking disparity in observed data led researchers to propose an astonishing alternative. These brilliantly radiant objects might not be galaxies, but individual dark matter stars, possibly with masses in the millions of times that of our Sun. Their models aligned JWST's infrared readings with predictions for theoretical dark matter stars powered by perpetual particle annihilation. JWST's data also matches expectations for primordial matter being drawn onto an annihilation-powered stellar entity. This hypothesis carries profound implications. If confirmed, it suggests that JWST is peering at colossal stars from the earliest cosmic epochs, rather than entire galaxy clusters with fusion-based stars. These dark matter giants could have reached a billion solar masses at their zenith. Substantial evidence is needed to confirm this extraordinary notion, but the prospect is spine-tingling, an eerie glimpse into the possible birth of the first dark matter celestial bodies in cosmic history. If the James Webb Space Telescope has indeed detected these theoretical dark matter stars, it would mark an unprecedented and Nobel-worthy breakthrough, a direct detection of dark matter powering observable stars. The team is actively searching for more dark matter star candidates in JWST's early universe data, strengthening the case for a new class of dark matter-fueled massive stars. JWST seems poised to unravel one of cosmology's greatest mysteries: dark matter's nature, revealing its ghostly luminescence in the infant cosmos. However, alternative explanations persist. Some argue these objects could be exceptionally bright fusion-powered galaxies or other exotic sources. Nevertheless, the dark matter stars hypothesis aligns with the mystery of supermassive black hole origins in the young universe. To confirm this remarkable discovery, independent validation of data is crucial, focusing on precise spectroscopic profiles for unambiguous evidence of these ancient anomalies as dark matter stars. The answers to this cosmic riddle may be hidden within these spectral clues. To confirm the existence of dark matter stars, researchers look for distinctive spectral characteristics. Legitimate dark matter stars should emit continuous blackbody radiation across a broad spectrum due to the sustained injection of photons from dark matter annihilation. This creates a smooth rainbow glow in the surrounding primordial matter. Additionally, these stars should display spectral absorption lines from accretion of hydrogen and helium on their outer layers, leading to dips in the spectrum. Helium absorption lines could serve as a unique differentiator from galaxies. In contrast, fusion-powered galaxies exhibit complex emission spectra due to their heavier elemental composition with structured patterns. JWST, designed for this purpose, provides a unique view of these ancient objects' wavelengths. Sensitive spectroscopic analysis in the infrared and radio wavelengths may capture the transition phase when dark matter stars shift from annihilation to fusion-based power sources, showing prominent blackbody and helium absorption patterns. Identifying these distinguishing spectral features is crucial for confirming the presence of dark matter stars over conventional galactic origins. In conclusion, as dark matter fuel depletes over millions of years, hydrogen fusion takes over in these stellar objects. Detecting objects transitioning between these two spectral types offers definitive proof of their dark matter ancestry. JWST's sensitivity allows us to witness this transition firsthand. The object's extreme brightness and high redshifts also support the dark matter hypothesis, as dark matter densities in that era could create such luminous giants rapidly after the Big Bang. Confirming dark matter stars would shed light on the origin of early supermassive black holes, suggesting that they formed through dark matter star collapse, an intriguing formation mechanism for these cosmic behemoths. The dark matter star explanation is intriguing but speculative. Further analysis of JWST data will provide more insights into these enigmatic relics. Regardless of the outcome, this underscores how new observations can revolutionize our understanding of the cosmos. JWST's images are reshaping astrophysical models, hinting at more radical discoveries on the horizon. It's an exciting time for exploring the cosmic dawn, with dark matter stars as just one of the intriguing mysteries waiting to be uncovered. What other celestial enigmas await our discovery beyond the stars? Feel free to express your thoughts and viewpoints. And be sure to join the Revel Discovery community by hitting that subscribe button to stay up to date with lunar revelations and the forthcoming frontier of space exploration. Remember, as we venture into the universe, the sky is not the limit. It's just the beginning. Keep looking up,